I'll start then. So everyone, I'm Carlos Ferrazza from ETH Zurich. And today I'm going to talk about an optical tactile sensor, which is based on a very simple principle. If we place a camera below a soft, transparent material, and we randomly and densely spread some tiny plastic particles within this material, once a contact force is applied, the material will deform and trigger the particle motion, which is tracked by the camera. The patterns created by the particles encode information about the soft material deformation, and therefore the force is applied to the sensing surface. Now, it might be that Zoom adds some lagging to my videos, but I hope it will be fine. But here on the left, you can see a prototype of our sensor with the camera inside the aluminum part and the gel in black. And on the right, this is the stream captured by the camera. And you can see that the random spread of particles does encode an extensive amount of dense information, which provides a very high spatial resolution. From the image stream, we aim to estimate the three-dimensional contact force distribution, which is a very versatile quantity that is suitable for generic tasks. And we represent this force distribution by discretizing the sensing surface over a finite number of bins, and compute the distribution as a set of three-dimensional vectors indicating the force acting at each of these bins. We then estimate the contact force distribution in a data-driven fashion, because such an approach can theoretically exhibit arbitrary accuracy, depending on the data provided. Essentially, compared to model-based methods, we don't have to compromise accuracy by making model simplifications to retain real-time tractability, but we just need to provide very accurate data. Additionally, these data-driven approaches generally show very fast inference times, especially if we make use of tailored learning architectures. Of course, we need to collect the training data, and I'm going to show how we do it for a supervised learning approach, essentially to go from the image stream on the left to the video shown on the right, where you can see in a color code the current vertical forces applied to the surface. For this, we collect our training data entirely in simulation. The first reason is that getting ground truth force distributions is challenging because there are no readily available sensors that provide this quantity without altering the contact with soft materials. And the second reason is that we save a lot of time in calibration experiments and avoid to wear the sensor surface before using it. So we simulate thousands of vertical indentations in a finite element environment. And for this, we represent our sensor with very accurate hyperelastic models, which we obtained via state-of-the-art material characterization experiments, of which you can see an example in this video. For each indentation in the finite element simulations, we extract the displacements of the material due to the deformation. And using a camera model, we project these displacements to optical flow features, which we include in our dataset. Similarly, for each indentation, we extract the three-dimensional ground truth force distribution, and we assign this ground truth label to the corresponding optical flow. Therefore, summarizing, posing the force distribution reconstruction as a supervised learning problem, we now have optical flow as inputs and ground truth force distributions as outputs, both obtained via finite element simulations. What we do on the real-world sensor is to just extract the optical flow from the images with a very efficient algorithm and predict the current force distribution. We train for this a tailored neural network architecture based on a slimmer version of UNet, using only the simulation data. We then evaluate the network on vertical indentations that we collected in real-world experiments, and we get an accuracy in the order of millinewtons for forces up to 2 newtons with a finger-shaped body. The network we used is therefore able to predict the 3D contact force distribution at 50 Hz on the CPU of a standard laptop. And an additional benefit of the simulation training is that we don't need to retrain our network on each real-world sensor, but we only need to extract the camera calibration parameters. I will finally show you the sensor running live now. For this, let me change the screen share. And also switch my camera view to the sensor, which you should see now. And you can see that if I make a vertical indentation with my finger, sorry, I have to start the application. Yeah. You can see that the three components of the force distribution are predicted in a sensible way. And even if we trained only on single contact indentations, the convolutional structure of the network makes it possible to estimate as well multi-contact cases, and even the contact with multiple shapes, different shapes. With this, I would like to thank you for your attention. And if you have any questions, we can discuss it later or in the chat box as well. Thank you.
Fantastic. I guess we've moved to the next, because no questions really with these, so we'll move to the next talk if that's okay. And we can do questions later. So that would be Janken.
Could you see my screen?
Yep.
Okay. Hi everyone, my name is Guanqun. I'm from Smart Lab of University of Liverpool. Today I'm going to talk about a spatial temporal attention model for tactile texture recognition. We are interested in tactile texture because it's one of the most important properties of tactile sensing. It conveys important surface characteristics and appearance of the object. It's necessary in robotics for manipulation like grasping or perception like classification. And also we are inspired by the human experience of tactile selective attention. For example, in the right figure, if we would like to distinguish a Lego brick, the stars on the green one will give us more clues than the flat region on the red one. And previous contact will give us prior knowledge for the later recognition. But for the texture recognition, previous works have been limited to treating all the regions in one tactile image equally or treating all the samples in one contact event equally. It's still hard to effectively extracting the discriminative tactile features. So we propose a spatial temporal model, attention model to solve this problem. The input of our model is the sequence of tactile textures collected by gel side during the contact event. Our model mainly consists of 3 parts: a CNN module that extracts spatial features from each input, and spatial attention that highlights the salient region from the CNN, and a temporal attention module that models the correlation between spatial regions in the sequence. In our spatial attention module, we first aggregate channel information using average pooling and max pooling. And then we use a convolutional layer to generate a attention map that highlight the salient features. For example, in the right figure, our spatial attention will highlight the regions for the with the red square rather than the green one. And for the temporal attention module, we first use 3 convolutional layers to convert the input into different feature space. Then we can calculate the similarity of all the locations in the input with the dot product. Our temporal attention could effectively model the relationship between different separated spatial regions. For the result, we test the classification accuracy step by step with different number of tactile images used in a sequence. And we introduce some empty tactile images as our noisy data into the dataset. We can find that our proposed method achieves the best result and our method is robust to the noise. At last, we visualize the heat maps activated by our attention mechanism. The image in the first row are the heat maps without using any attention mechanism. The images in the second row are the heat maps activated by our spatial attention. We can find that more contact regions are activated by our spatial attention. For the temporal attention distribution, we randomly choose a region and select top 3 most relevant regions in each texture. We can find that some of them located in the latest contact region, and it means that our temporal attention could make use of the latest information for the recognition. And That's all. Thank you for your listening.
Thank you, Guanjing.
Thank you.
Fantastic. So I guess what can we shall we work back in time, and we could do questions first on these, and then we can move to questions for Vincent, or would you prefer the other way around? Vincent, are you okay? Vincent's muted. Shall we do questions for these for these two lightning talks, and then we'll see if there's other questions as well for the other speakers. Yeah. So Shan, you had a question.
Yeah. Is Vincent on? And I'm a bit concerned Vincent can't hear us.
Maybe we'll start with questions then for the people who did the short talks.
Sorry?
Because Vincent doesn't seem available, so maybe if we start with questions for the people who did the short talks.
Yeah, yeah.
So
we have some
question.
Yeah.
Yeah.
Okay, so a question to Carmelo. I unfortunately didn't, I put all effort onto listen to your talk, so I was distracted by other things. But if I remember correctly, you were looking into modeling your material and modeling the optical flow, if I remember these bits correctly. But then you also use a neural network for further processing. So my question is, I mean, to what extent do you actually need a neural network? Could everything be done just with the, let's say, more traditional modeling using expertise on materials and geometric behavior?
Yeah, so it depends a bit. So from the images, right? From the images, from the optical flow, we just have information, right, about the deformation or the force, but we don't have actual force distribution values. So we put the network in the middle between the optical flow features and the force distribution. Now, the fact is, you can replace this network, as you said, with some modeling, but for having modeling that works like in real time, you need to make some assumption, which usually is the case for the linear elasticity assumption. However, when you start doing like large deformations, then the force values start to not match anymore with your linear model. We in the work where we introduced these ground truth labels for the force distributions, we also evaluated how different it is to use an hyperelastic model compared to just a linear elasticity model with just the Young modulus and the Poisson ratio. And the difference, like already for very mild indentation, was up to 40% in accuracy.
Okay, good.
So the reason to use the neural network is to have like a very general representation, which is the force distribution, right? That you can apply to multi-contact or several shapes, but try to do it in a very accurate way.
Okay, and just to check on that point, so you're not using the models at all. So you go straight to the neural network to do the whole.
We use the models to generate the data in simulation, essentially. So we use an hyperelastic model in simulation to generate the data for our application.
And then you use the neural network to refine that?
No, so okay,
two different avenues you go, yeah, okay.
So in the simulation, like we have a finite element model, like an hyperelastic model, which we use to perform these indentations, like thousands of them.
Yeah.
And for each indentations, we compute on one side what the camera sees, so the optical flow features, and on the other side, we compute the force that the indenter is applying, the force distribution. And the neural network is used to map from these features to the force distribution in real time.
Okay, okay.
Because the finite element simulations are not real time; they take hours. So
too slow. Yeah.
Yeah.
Okay.
Maybe I have one follow-up question
yeah.
to Kaspar's previous question. I think it will be a common question to all the sensors that use silicon. So because if we use the silicon for sometimes the silicon may degrade and the modulars may change, and you have to moderate. You have to use your network to train another data set. Is that true for camera? And is there any solution to this problem? Okay.
Yeah, I mean, I think that is definitely generally the case. And I mean, that is one of the disadvantages of using silicone rubber.
Yeah.
And I suppose independently of whether you use neural networks or whatever, I mean, also if you have more traditional models, you would need to adjust your parameters over time. I haven't heard of anyone actually investigating that actively to see whether one can somehow model the behavior of that material over time. That would be interesting. Yeah, definitely an issue.
Yeah.
I think Yahaya wants to say something.
Thank you, Carmelo, for the nice presentation. So yes, with regard the silicon, we have like different type of silicons. This is we have experience with, and also their relaxation time is different, and they have time warping and all of these things, which is making different silicons not easy subject or easy things to benchmark against. So my question to Carmelo, please, when you did the finite element analysis, so you did like indentation experiments, then you did simulation. So you have used the experiments to validate the simulation. Then once you finish this one, you generate big data for different scenarios using simulated data to train the neural networks. Am I right or wrong?
Yeah, that's correct.
Now,
So,
regarding scenarios, you didn't do experimentation for, and you did simulation. How did you make sure those results, what you get from simulation, are correct?
okay, so the way we obtain the models is not by indentations. So as you saw, like for example, there was this inflation experiment. So they are like completely different experiments. This is like state of the art. We collaborated with a group here at ETH Zurich, which works on mechanics of soft materials. So we really got like the best model we could get for a static case, right? We didn't consider, for example, hysteresis or wear. So for that, you would need a different type of model, although you could do it. But for static model, this was really the best we could do. Then what we do is to perform a short set of real world indentations and just match in terms of the total force. So because that's the only thing we can compute, right? We just attach an ATI sensor. And the resolution, the precision we got on this is just lower than the resolution of an ATI sensor. So it was in the terms of millinewtons again. So that's the only validation you can make.
Is it 2D or 3D you have done?
You mean in the
force?
In the force, 3D. We made the vertical force and both the horizontal forces.
Okay.
Of course, we only made vertical indentations. Therefore, the horizontal forces are a bit much smaller than the vertical forces, but they were still matching.
Great. Actually, I've got a quick question. You've got a lot of interest, Carmelo.
Yeah,
so maybe I'll ask a last question, and then we'll move to Vincent, because we want to ask him some questions. So presumably, if you use an optic flow, I guess you're basically feeling the local shear. That's what you're extracting with your sensor. So which is great. That's kind of like how the human sense touch works. So I was wondering, do you use a very high resolution image as input to your CNN, because your particles are very small? I was wondering, I mean, we use a low resolution image, I should say. We only use 100 pixels square, but so what resolution do you use?
So what we did is, so what they thought in the start was, if we use a random pattern, we're going to have issues like when you change from sensor to sensor. So we thought we make very small particles, and you can even get smaller than this. But we make like we average the optical flow into bins such that you have more particles. So in the end, the optical flow image is like 40 by 40. So you get, I don't know, a bit more, like 1,000 pixels.
Great. Yeah. No, cool. That's good. Right. Fantastic. So shall we move to ask Vincent some questions, and then we could ask Casper, moving backwards in time?
Yeah. I saw you have one question in the chat box. Shall we start from yours?
But mine,
Yeah.
again, unless you don't want to answer it, Vincent. I basically had to, well, you know where the question is anyway, Vincent. Ooh. So Vincent, I was asking about the Patinian corpuscles and the relationship to your tactile waves.
Yeah, go ahead. Yeah, I was saying that actually, for sure, I mean, every thing that was done about the Patinians shows that they would be first in line if you want to collect that information, but it's highly probable that any others could. It has to be verified, but there's no, you know, for example, one thing which is very clear is that, you know, in the tradition, the different type of receptors, they are put in boxes, but the actual physiology is not so clear at all, actually. If you go in the lab and you measure them, they don't fall in boxes at all. For example, something to be said, there is a conflation, often the notion of adaptivity and frequency tuning are conflated. It's not at all the case. And also the, you know, being adaptive is one thing, like they would, you know, respond to transients and, or, you know, get adapted very quickly to a persisting signal is one thing. It has really nothing to do with sensitivity to different frequencies. In fact, there is absolutely no trace of specificity according to frequency. And even the Merkels, they are really crazy. They are really, really sensitive, in fact. But of course, they take a long time to adapt, and so that's the way they are, you know. And I don't think there's a very simple way to associate them to functions. It's not that clear at all. It really is the result of a very long evolutionary process, which has no final, you know, goal. So that's Patinians are deep, as far as I can tell. There's quite a few studies that, you know, anatomically that show that. Some are there on the skin too. They're kind of opportunistic. They tend to also be found near blood vessels. That's kind of interesting. Why blood vessels? Maybe because there is an advantage in having them simply because of the acoustic properties. Who knows, you know? They also tend to be found in clusters. So that's interesting. That's actually much more interesting that they are found in clusters. That's also true, actually, of the. Actually, there's been a couple of new studies on the neuroanatomy of the hairy skin, and it's really, really very different from the little pictures you see, you know, in the textbook. The hairy skin has it's really, really. I didn't know, actually. It's very remarkable. The Merkel cells, which we have many in hairy skin, they are assembled in domes, like clusters, where you have many of them, and each dome is very far away from the others, like centimeters. So it's really it's really not a good idea to look into, if you want, textbook representations, because they are based on no assumption that were made like 40 years ago, and with modern, modern techniques, it's quite a different picture actually that you get of the at least of the periphery. And so that's what I would say. It doesn't really matter actually at that level of analysis.
Cool, fantastic. So I think Shan, you had a question as well, didn't you? I saw.
Yeah, I do have one question. So because we have talked a lot on robotic tactile sensors, but for human tactile sense, sometimes it's like a black box because it's hard to map our human brain, and we don't know what's going on here. Right. So my question is there any way to measure the human tactile sense? So using sensors or other measurement ways, and how to compare such sensors against the robotic tactile sensors?
Oh, so the question is, how do you map?
Yeah.
Well, my hunch is that actually you have to start from the basics, like the mechanics, and like collisions, friction, what the squeezing, things that are useful, for holding objects, telling what they are, where they are, and to function that you need to have. That's really the best way to go. But for example, it's interesting in vision research. There was a lot of research in the 80s and 90s and 2000 for making foveal optical sensors for robotics, and it doesn't have caught on so much actually.
Mm-hmm.
And the reason I don't know. The reason is because I suppose the technology available for consumer products really drives what you can do in robotics, and so that's really the a much bigger driver than going for the optimal design. I mean, the cost is availability is really important actually.
Yeah,
it's true actually in natural systems. I mean, the Pachinnon was not invented for humans. It was invented a million years ago for completely different animals.
Yeah.
So yeah, the anthropomorphic view is very misleading for sure.
Can I add a question here? Maybe, I mean, extending from that, I think, from that discussion, but also maybe looking at it from a more practical point of view, and also very much in line to move towards developing technology. So, I mean, tactile sensing is more complicated than many people think, including me, I suppose. I mean, many roboticists just look at forces and force distribution. But as you have said many times, Vincent, many more things are happening in the fingertip when we touch things. So you mentioned sweat, for example. Temperature is also a very important thing. So I'm just thinking, why not explore that further and create tactile sensors that incorporate that measurement of the information as well. So, for example, when I touch a glass, it's very different from touching a piece of wood, even though the surface might be very smooth, but just by the temperature, I can straight away say, okay, yeah, that is now wood or that is glass. What is your view on that?
Well, thermal sensitive elements are really easy to make. because actually it's actually whenever you make any type of mechanical transducer, it's really hard to make it insensitive to temperature.
Good point. Yep.
So why not? You know, I mean, thermal resistors are really easy to embed, and you could also do really simple things like having 2 electrodes in a rubber finger, and then basically extract the diffusivity of the object that you are touching through a fairly simple measurement.
Yeah. Because I mean, if we would explore that further, or actually actively pursue that idea or these ideas, I think classification of objects would
for sure.
become much easier.
Something that would be good actually is to make a finger with a little heater inside. Because that's how you tell, you know, what materials are is through their diffusivity, like how fast the heat propagates.
Yeah.
And that's really informative. Like there is an example that's well known is if you take a pill box made of metal, okay, of course it's hollow, right? But because you know already it's made of metal, then when you put your finger on it, you know it's hollow. So you get a lot of geometric information from thermal inputs.
Yeah, yeah, yeah.
This might happen anyway as optical tactile sensors get smaller, because you know the cameras, they get hot, they have lights inside with LEDs, and they're moving closer and closer to the skin. So you know, our sensor gets hot. You know, so
Yeah.
the natural thing.
So you have a heat source, so you can have diffusivity. Yeah.
Yeah, I will look into that. Thank you.
I've got a question from Sanat Kapsov. So he said, I attended your Atronica lecture. He said because of Zoom issues, he couldn't see the videos and hear the sounds. And they would really like to see them, as I think many of us would as well. Are there ways to share them, the videos? Because we didn't see them clearly in your talk today as well. And I guess also, I mean, you mentioned the lectures. How do we get to them? I'd like to see them
It's
as
on
well.
YouTube.
Oh, they're all on YouTube.
Yeah.
Can you
Just
share
look
the
for-
link in the chat box? It would be great.
Yeah. Let's see. Yeah. I'll do it right now.
I think you only need to go to YouTube and type Vincent Hayward, and you are there.
Yeah, it's there. Yeah.
I found it. It was very easy.
Cool. Right, good. I can't see if there's any more questions for Vincent. If not, I guess we could
It's
move
the
to...
benefits of the lockdown.
Hello, everyone. Thanks.
Was that a question? No, I don't think it's somebody saying goodbye. Shall we, if there's no more questions for Vincent, shall we move to Casper? Yep, cool. So
I tried to respond already to the questions in the chat box, but if there are any further questions, or if anyone wants to have further explanations on that.
Yep, Zaya.
Thank you, Casper, for the nice presentation you have done today, and with your colleagues also. Thank you very much. My question regarding the force estimation and the combination between tactile and force, do you achieve real time in order to do this one for certain robotics application, or is it still offline, or is it real time?
Real time, real time. So what you saw in the videos is in real time at normal time, nothing sped up or slowed down. And it is just the processing of the camera images that we have to do. So we are limited by the frame rate of the camera. So if our camera has 20 frames a second, that's what we can achieve.
So in terms of latency, do you go to like part of the second, or you go down to milliseconds? So what's the latency range of the sensors, combined sensors?
Well, I mean, it's dictated by the frame rate. So they come in at, the images come in at 20, roughly 20, it depends on the camera, 20 per second. And our processing is, I mean, there's not a lot of processing needed, because we can now, through a geometrical analysis effectively, and a calibration, find out what the force values are and have them within that frame rate. So that is not a problem. So if you want to speed things up, you need to have a faster camera. And let's say you go to 100 Hertz, that should be possible. But you will, and I think the processing of the data is done so quickly that can be still done in 100 Hertz, no problem.
I assume also you have dealt with different object size and maybe also different material, or you stick to certain type of object size or shape and material?
So for the objects that we are getting, I mean, we are measuring, so to speak, they have to be, of course, in the range of our sensor. So I mean, we have focused mainly on very small objects, you know, like the USB connector there, because they fit within the, you know, the opening, so to speak, of our sensor. I don't know whether we have looked at larger objects. We could hold our sensor against larger objects and see whether there's an edge, for example, or a sharp corner on an object. But obviously our tactile, you know, the area is what it is, and we cannot measure beyond that. Then we would need to, you know, do multiple, you know, measurements on a larger object.
Yeah, you mentioned regarding the size, but also my question about the shape and the type of material, solid or soft or semi. So
our main focus was on, I mean, this is still work that is happening. So fairly rigid objects. I mean, what our sensor does, it's very similar to other sensors in that area, is effectively looking at a deformable membrane. And so the camera effectively just sees what is being pressed on there. And we can achieve quite some fine detail there, but that is very much in line with, you know, with the other sensors that we have already heard about, but we'll also hear about later, I think.
Cool. I've got a quick question. So on the combined force and tactile sensing, you have these force pins. Where were they placed? Were they placed on kind of the more, not on the elastomeric, on the soft part of the sensor, but on the hard part? Is that right?
Yeah. So that was in the earlier version of our system, where we had this kind of separation between the soft part in the center and the more rigid force measurement areas on the side, and that worked reasonably well. But so effectively there was really a big difference between you touch it in the center and having virtually no force being applied to this fairly rigid deformable structure, and then or you went to the outside and you measure forces, but then you didn't measure any tactile information. So now the new system has effectively the whole area on top is sensitive to the tactile information and also transmits the force information. So in this way, we can now use the whole surface on top to measure both. And if you have remember the images or the video we have shown, you have effectively now a camera image that shows the tactile information, and then superimposed you see the 3 to 6 kind of pins or force information areas that come through, and we have to, of course, then separate that out when we do the image processing.
Oh, cool. Yeah, no, I really like the design. I think it's fantastic. So I was kind of thinking because you can, from the tactile image on just the pins, if you label it with the force, you could construct a model to infer force just from the tactile part of it, not the force pins, but those
Yeah,
bits.
of course, and that is, of course, also a very good approach. And what we found is that we can improve on the accuracy there a lot. And you have seen the data that I've shown in my presentation. So we come closer to the ATI sensor then others can achieve that. And on top of it, we can do it in a simpler way because our system is tailored to measure the forces. While someone, you use neural networks, and then obviously that is your way of, understanding what is this tactile information. Yeah. So these are the main points that that we can observe in our system.
Cool. That's so that's kind of like using the morphology of the skin to get it to sense force better. Yeah, no, it's honing the morphology of the skin appropriate to what it's trying to sense, which is cool.
Thank you. Yeah.
Cool. Are there more questions for Casper? What do we want to do now? I mean, I'll answer that. I'm happy answering the questions for me on the chat thing, unless anybody has some burning questions.
Maybe I can just link to that because I had that question in mind to you, Nathan.
Okay.
So it's about neural networks, and I mean you're using them heavily there, and you have good results at the end. But obviously that you have to go through an enormous training process. Okay, good, reasonable training process. But again, the question is, could you achieve something through modeling? I mean, could you maybe look at the geometry of the thing, maybe look at the elastic behavior of your materials and already push it to a certain level, and then maybe use your neural network on top of that? I mean, is that something you have looked into?
I mean,
yeah.
Potentially. So the difficulty we got was, as I say, this shear. When you've got, if you've got tactile sensor interacting with the forces with a surface, the forces of that interaction, basically interfere with what you're trying to perceive. So maybe that be the surface shape or the pose of the feature. And we found that really hard to separate it. And so a neural network is admittedly a brute force approach for that, but it worked. So would it be possible to model the shape otherwise? I think so. I mean, modeling it requires quite a lot of person investment to construct these kind of finite element models. And whereas a black box method such as a neural network, it takes a lot of computational time, but it's relatively simple to set up. So I do think, the modeling approach would probably work as well, but the effort of doing it. There may be other things, like other features you can extract from the tactile image that may not be, if you like, as polluted by the shear information. So that's another approach that could be tried.
Okay, yeah, thanks a lot, very good.
Okay, do you have any other questions? I think I have chased up in the chat box. I think we have answers at least almost all of them. Any other questions?
For any of the speakers today?
Yeah.
So I may have a question, please, to Nathan, please. Okay. So at the end of your presentation, you have mentioned dynamic vision sensing system, and this is the field I am working in since now 4 years, and that particular problem. So we did the slip estimation, force estimation, and we are combining them, and we are also using neural networks to go down to microsecond time latency in terms of rapid grasping. So what's your view in this line?
Benefits of event-based tactile sensing for optical tactile sensing. I mean, we're going to see more. I mean, as you say, you do it, we do it. There's a couple of other labs that do it. I mean, I guess there's a couple of. I mean, in terms of the field, I mean, event-based optical tactile sensors lagging behind because the cameras aren't miniaturized as undergoing the rapid miniaturization of conventional digital cameras. So there's, if you like, a lag there that needs to be overcome. But I think that's coming. So then you will see more labs use event-based optical tactile sensors. The principal benefit, as you say, I mean, in terms of the technology, obviously there's things like the power consumption and all these other aspects. But I would see the benefits of technology. One is the latency, as you say. I mean, you say microseconds, but you can easily, I mean, these things have an underlying clock rate of a megahertz. So you can potentially, down to microsecond temporal features that you can detect. That's one important aspect, which I think will come through, particularly in, like, say, the dynamic touch aspects that Vincent is mentioning. I think the other aspect of it, which Ben Ward-Cherrier, who's the guy who did the work, on it in the lab, and this guy pushing this forward, is that it's more biometric. We don't use digital transmission in the body. We use spikes that have, in some aspects, some, if you like, analog aspects in terms of the timing of spikes. And so if to move the field closer to, if you like, human touch, you've got to use a kind of representation that's more like how we represent information, which is analog through spikes. But then there are challenges of this as well, that it's not so easy to throw a convolutional neural network at this, because people haven't really got that working on event-based stuff. I mean, you can kind of do it, but you can
accumulate a few like polarity or events in a frame, but in very short frame, then you can do the conventional things. Yes, but the other issue, of course, as maybe you are familiar with, the noise level, and you have to get rid of this. And whenever you go in the resolution, very high resolution, then the noise become significant. So
exactly. So one way is to convert it back to a conventional digital coding, as you said, and then you can still get a very high frame rate. But I would say that to really take advantage of it, you need spiking neural networks. And
excellent. I think this is excellent idea. Yes.
And the field just isn't there at the moment, but it will get there probably fairly rapidly, because there's a lot of acceleration from the visual event-based vision. That's a very active field of research.
Yeah, I think I have one comment following on these previous questions. So like the accurate force measurements and also the data from optical tactile sensors. So there's a question whether we really need the very accurate force sensing to determine the force values. So for example, if we grasp something, I can't tell how many newtons I apply to the glass. So sometimes we just have a rough idea. So maybe we have the data, we can interpret and feed the data into the action directly. And maybe we don't need to estimate the force very accurately. Just some thoughts.
Yeah, I think in terms of force, yes, but in terms of incipient slip detection, it's important to have the incipient slip at maybe in certain application millisecond, even microseconds, because you want to have early detection for the incipient slip, and this is where the dynamic vision will come on board. I agree with you in the accuracy of the force measurements. Thank you.
Yeah.
It's probably very task dependent what you need the accuracy for. Some tasks don't need high accuracy. Others do. There's papers that saying we can feel like micronewtons or micron accuracy, of indentation in some circumstances. So, it's what you need to use it for.
Yeah. Okay, I think it will be the lunchtime for some of us. So I would like to thank all the speakers in the morning sessions very much for your great work, great talks, really inspiring. And we have seen a lot of discussion, inspiring discussion in the chat box as well. I think we should thank the speakers again. And also, I would like to thank as attendees as well. I can see there's some attendees who are in the midnight for now, so who attended the workshop at 3 a.m. In the USA. I think that's the fact we have to tackle these time differences. We should also thank the attendees for attending our workshop. So we will start the afternoon sessions at 2:20 in the afternoon. And we will have 2 other sessions in the afternoon, and we will have a final discussion session at the end. So we will welcome all the speakers to join us for the live discussions. So for example, we already have these live discussions after the morning sections, but I believe in the afternoon, we will see more discussions later. Okay, so time for lunch. So I will look forward to seeing you later.
Yeah, thank you.
Bye. See you later.
Bye.
Thank you.
Bye, everyone. Bye.
I will leave this Zoom meeting on, and people can keep sending their questions, general questions there. Yeah.